Study of complex numbers. Complex numbers are a combination of two terms, one being a real number and one being what's called an imaginary number. We've been working with real numbers. You've been working with real numbers all your life. We're going to introduce now the concept of an imaginary number, put the two together and form what's called a complex number as we go through this section. Let's talk about the first definition. The first definition says the square root of a negative 1, which we've not been able to deal with in the past because there is no number that you can multiply times itself to get a negative 1. So we're going to define that as the letter I. And with that, we know that the product of radicals says that if we squared both sides of this equation, then we would have that I squared equals a negative 1. This is the premise of the study of imaginary numbers and the study of complex numbers. And you've got to memorize these two thoughts. With that, let's take a look at simplifying an expression under a radical that has a negative number. I want to rewrite this as something that's in terms of I, and I must do that every time when I have a number underneath the radical that's negative. So what I want you to think here is to think of the square root of a negative 1 times the square root of 11, because their product is a negative 11, and we've just defined this as I, so I'm going to write this as I times the square root of 11. Our textbook will write this sometimes as the square root of 11 times I. You won't see me write it like that. You're going to be taking this test paper pencil, so I'm going to be able to see it come from you either way, so it won't matter. Now when you take the sample test, I don't know if it's going to mark you wrong by chance for putting the I in front of the square root of 11 versus the square root of 11 and then the I. Your dilemma is going to be when you use the computer and you write these, that if you don't stop this radical symbol and then put the I, it will certainly mark you wrong because that is incorrect. That I has to be outside of the radical. That's why I prefer to put it in front. If I have a perfect square, the square root of a negative 25, think of it as this. The square root of a negative 1 times the square root of 25. This is I, and this is 5. So we might write I times 5. I prefer to write that with the numerical coefficient in front and write it as 5i instead of I times 5. And as you continue to do problems like this one, in my opinion, there's no reason to write this step. I know that I've got a negative sign underneath the radical. This is a perfect square. This is just equivalent to 6i. Or the square root of a negative 100 is just equivalent to 10i. Do those conversions quickly. There's so much other work to do here. Don't spend time on this. This should be something that becomes very natural for you. Now, if I were to put a sign in front of the radical, while this is equal to 7i, I need you to remember that I'm asking for the opposite of that, or a negative 1 times that. So I need a minus sign in front of that 7i. And if the number is not a perfect square under the radical, and I'm asking for the opposite of it, let's pull this negative 1 out from underneath the radical. I've got out in front this minus sign, and then the square root of a negative 1, which is inside here, is I, and then I'll have the square root of 13 under the radical. I prefer to see this like this. Again, the book is likely to maybe write this like that. Negative sign in front, opposite of the square root of 13, times the letter I, as long as that I is not under the radical. That's another good way to write this expression. Just another problem or two involving the square root of a negative number. But here I want to remind you of simplifying. So, and you decide if you need to write all of these steps. I think about that first, because there's a negative sign underneath, and then 25 times 2 is equal to 50. This is 5, this is I. I prefer to write that as 5i in front times the square root of 2, instead of 5 times the square root of 2 with the I in back. But that's correct as well. One more time. Let's take the square root of a negative 200. So I need you to think of the square root of a negative 1. I need you to think of the square root of 100 and the square root of 2. That product is 200. Here's the negative sign that's underneath the radical. This is I. This is 10. So I'm going to write it as 10i times the square root of 2, or 10 times the square root of 2 with the I in back. The complex number, now I've mentioned it already a little bit before, is composed of two terms. It's composed of a real number and an imaginary number. And the definition is in the book. It does say that their coefficients could be equal to 0. In other words, one of the terms could be missing at any time and you still could have what's called a complex number. But typically we look at complex numbers as two terms or as a binomial. And what I'd like to look at now is adding two complex numbers. Here's an example of a complex number. 7 plus 3i is a complex number. Here's the real part. Here's the imaginary part. You add them together to make what's called a complex number. It's really quite simple. It's a binomial, is all it is. What I want to do is I want to take this complex number and I want to add to it another complex number, a -4 plus 8i. And all I'm doing is using my algebra. As a matter of fact, this whole section is quite simple because I'm just using my algebra skills. Adding, combining my like terms. When I subtract, I add the opposite. When I multiply, I'm going to be distributing and foiling. So it's very much the skills that we already know. So what I'm going to do is I'm going to collect my like terms. So I'm going to collect this 7 and -4. They add to be a +3. And then I'm going to collect the 3i and the 8i, their like terms. They add together to be 11i. I'm done. I've added those two complex numbers together. Let's subtract. If I had a -5 minus 4i, and I wanted to subtract a -11 plus 3i, complex numbers are always written in this form, the real part first, then the imaginary part. So it seems a little bit awkward. We're used to seeing the letter terms in front. But if I'm asking you to subtract a complex number, I'm asking you to add the opposite of these. I'm going to write this down so that we see that. I'm going to ask you to add, I'm going to use color here, I'm going to recopy this -11 plus this 3i. And when I say add the opposite, this has got to become a positive, and this has got to become a negative. Only that binomial, because when I subtract, I'm adding the opposite of this one. The -5 minus 4i is the same. Now I'll collect my like terms. So I've got a -5 and a +11 that add together to be 6. And then I'm going to combine a -4i and a -3i, which adds to be a -7i, and we're done subtracting. We've added the opposite. When we work with imaginary numbers, square roots of numbers that have a negative value underneath the radical, we can't use the product rule with radicals. We always have to put these factors into imaginary form first. So we have to pull out the square root of a -1 out of these, rather than, so I can't take this -3 times this -7 and get a +21 and be done with it. That's not a true statement. What I have to do is I have to call this right here I times the square root of 3. I pulled out the square root of -1 out of that. And then this one I have to call I times the square root of 7. And now I'm going to multiply these. I truly am going to multiply. And remember, multiplication can be done in any order. I times I is I squared. The square root of 3 times the square root of 7 is the square root of 21. And you need to remember this. If I is defined as the square root of a -1, then I squared is equal to a -1. And I'm going to replace this right here with a -1. You can either write it as a -1 times the square root of 21, or many of us just write a minus sign in front of the square root of 21. This expression is not equal to a square root of 21. It's equal to the opposite of the square root of 21. Here's another example that almost makes it a little bit more clear. If I took the square root of a -64 times the square root of a -9, I need you to put that in terms of I first. This right here is 8i. And this right here is 3i. Now you're just multiplying two monomials together. 8i times 3i is 24i squared. That's all that is. And whenever I have a term that's got an I squared with it, I drop the I squared and I replace it with a negative sign in front of that value. So this 24I squared, I get to drop that, and it's because that's equal to a -1, and the value of this expression becomes 24 times a -1 is just a -24. So again, it was 24I squared. I normally just drop that. Look, I have left a 24 and put the opposite sign on it because I want a -1 times it, and I'm done. Always take imaginary numbers and put them in terms of I first, and then do the process, whatever the case may be. In this case, it's multiplication. More multiplication with complex numbers. What I'd like to do now, though, is I'd like to take a monomial times a binomial, and I treat it just like I do algebraically, as though I have x's in my expression. So I'm going to take 5i times a negative 2. It's almost like taking 5x times a negative 2. That would be a negative 10i. And then 5i times 4i is 20i squared. And finally, all I'm going to do now is I'm going to replace this I squared with a negative 1. And 20 times a negative 1 is a negative 20. Now I'm going to put that term in front because I like my real term first. I'm going to put my imaginary term in the back, the minus 10i, and I'm done. You've got to remember, though, that whenever you see I squared, you must replace that with a negative 1. Basically drop it off, change the sign. And finally, we turn to foiling, to taking two binomials, two complex numbers, and multiplying them together. So I've got to multiply the first terms, then the outer terms, the inner terms, and the last terms, and combine my like terms. So first I'll have 3 times 7 here is 21, and 3 times a minus 5i is a minus 15i, and then right here, 2i times 7 is a positive 14i. I'm going to locate it below this term because those are like terms, and a positive 2i times a minus 5i is a minus 10i squared. And what I'll have then is this 21, and a minus 15 and a plus 14 is a minus 1i. I won't bother to put that 1 there. And a minus 10i squared is a plus 10. Drop the I squared. You've got to remember now to come back and to collect this term and this term because they're both just real numbers. Add them together. They add to be 31 minus I. That is the result of taking these two complex numbers and multiplying them together. I get another complex number. You should always end up with two terms. That I squared term always disappears because you get to take the opposite of it, drop the I squared, and it gets added to the real part. In this very chapter, when we were rationalizing the denominators and we had binomials downstairs, we multiplied top and bottom of that fraction by what was called the conjugate of the expression. This complex number has a conjugate, and its conjugate is this 4 plus 3i. Like with radicals, when I look for a conjugate, I'm looking to just take the second term, this minus 3i, and change it to a plus sign, to this plus 3i. This is why. It's because when I multiply a complex number by its conjugate, I will always get a real number as an answer. The I terms totally disappear. Watch this. When I FOIL this, 4 times 4 is 16, and then here I have a 12i, and here I have a minus 12i, and here I have a minus 9i squared. Well, do notice those middle terms, that outer and inner set of terms. Because I'm multiplying a complex number by its conjugate, those are always going to be the same but opposite in sign. So they'll always add to be 0. So what I have here is a 16 and a minus 9i squared. But remember, I squared is a negative 1. So a minus 9 times a minus 1 is a positive 9. And what I'm left with here is 25. Again, I promise that when you multiply two complex numbers together, one is the conjugate of the other, that you will always get a real number. The I terms will disappear because the middle terms add to be nothing, and that I squared term will be a real number, and it will combine with the first. This is a simple problem, but I just have to share it with you because I have some of you still making this mistake. Whenever I ask you to take a binomial and square it, I want you to multiply that binomial times itself. Many people will take this problem, take a 7 and square it and get 49, and they'll take a minus 4i and square it and they'll get a positive 16i squared. That's not right. You need to write this out 2 times. So we have 7 minus 4i times 7 minus 4i. And then FOIL this. So 7 times 7 is 49. And then I have here a minus 28i and another minus 28i. And this minus times this minus is a positive 16i squared. So while you do get the 49 and you do get the 16i squared, which is a minus 16, remember, replace that with a negative 1, multiply it by 16, get a minus 16. In the middle here, you're going to get two terms that collect to be a negative 56i. So finally, I'll take this 49 and I'll subtract 16, and I'm going to get 33. I'll bring down the 56i, and I do have an answer that's a complex number. Real part first, imaginary part second, and I've finished this process of squaring that binomial. We're going to go on now to looking at the variable I raised to powers. Powers other than I squared. That's the examples we'll come back to next. I'd like you to see some patterns that occur with the variable I raised to a power. We've established the definitions that I equals the square root of a negative 1 and I squared equals a negative 1. I'd like to establish about 3 or 4 more variable I raised to a power so that you can see the pattern that exists. Let's look at I to the third power. I to the third power is the same thing as I to the second power times I to the first power, because when you multiply you add their exponents. And so I decided to use this 2 and this 1, it adds to be 3. And also, I squared right here is defined up here as a negative 1. So what I have is a negative 1 times I to the first, or just a negative I. So I can define I to the third power from now on as being equal to a negative I. Let's go to I to the fourth. When I have even exponents, I like to think in terms of 2 as my exponent to prove this. So I'm going to look at I squared times I squared because those add to be 4. And I know I squared is equal to a negative 1, so each of these right here I'm going to replace with a negative 1. So I'm asking you to take a negative 1 times a negative 1. Well, that's just a positive 1. So we just defined I to the fourth as always being equal to the number 1. If I continue now, and I look at I to the fifth, I personally prefer to write that as I to the fourth times I to the first, because this is such a nice number. I know that anything that has I to the fourth in it is going to replace with the number 1. Well, 1 times I is just I, and I to the fifth brings us back to where we started, right here. And I to the sixth, I would write as I to the fourth times I to the second, because those exponents add to be 6. This is equal to 1. And I to the second is equal to a negative 1. So I to the sixth is equal to a negative 1. Well, so is I to the second equal to a negative 1. Again, watch. I to the first, I to the fifth is the same. I to the second is a negative 1. And I to the sixth is a negative 1. One more time. I to the seventh, I'm going to write as I to the fourth times I to the third. I to the fourth is 1. I to the third is a negative, a negative I. And what I have here is a negative I, and I've just found out that I to the seventh is a negative I. Well, I to the third was a negative I also. And I to the eighth, I'll describe as I to the fourth times I to the fourth, because those add to be 8. But I picked those because they're so nice. I to the fourth is equal to 1, so they are equal to 1 times 1, which is 1. And I've just discovered a pattern again. I, a negative 1, a negative I, 1. I, a negative 1, a negative I, 1. I, a negative 1, a negative I, 1. And the pattern continues. It goes in multiples of 4. Here's I to the fourth power, here's I to the eighth power. I to the 12th power would be equal to 1 as well. So but I to the 20th, anything that has an exponent here that is divisible by 4. So what we're going to ask you to think about next is, what is I to the 48th power equal to? And you're just going to tell me that that's equal to 1. Because I could write this as I to the fourth times 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 I to the fourth 12 times. But I to the fourth is just 1, so it means 1 times itself 12 times, which is just 1. And then we go a little bit harder, and we ask you to take and simplify I to the 57th power. And so I'm going to write that as I to the 56th times I to the first. And I chose 56 here. I have to choose something that's smaller than 57. These two have to add to be 57. I'm going to always choose an even number that's below 57. And I'm going to choose the even number that's divisible by 4 that's below 57. This one is. Otherwise, I would have gone to, if I didn't use a 56, I would have gone to a 54. One of those two even numbers would be divisible by 4. But 4 goes into that evenly. So I know I to the 56 is equal to 1 times I. And so I just simplified I to the 57th. It's equal to I. I to the 103rd. I'm going to write it as the product of two bases with I. I have to pick two numbers here that add to be 103. One of them's got to be an even number just below 103 that's divisible by 4. So it's either 102 That's the number that's just below it, or it's 100. And 100 is the number that's divisible by 4, so I need 100 and I need 3 as my exponents. That right there, because that exponent's divisible by 4, is equal to 1. I've already defined I cubed to be equal to a negative I, so I have 1 times a negative I, and that expression is equal to a negative I. Again, we can continue. One more example. I to the 42nd power, I'm going to write as I to the 40th times I to the 2nd. This is the even number that's below 42 that is divisible by 4. This is equal to 1. I squared is equal to a negative 1. This expression right here is equal to a negative 1. A lot of examples here. There's 4 different examples here. To I to some fairly large power, my goal is always to write it as the product of 2, where one of these is divisible by 4, and then these two exponents have to add to be my original exponent. We'll simplify some more expressions next, but they'll be binomial. In this problem, I just like to simplify this expression. I have to think in terms of I raised to the 4th power. I need to mention to you that our book doesn't quite present it this way. Our book thinks in terms of I squared, because I squared is equal to a negative 1. I like to think of it in terms of I to the 4th, because I to the 4th is a positive 1. I find that to be simpler. You have to decide. This is the way I like to present this topic, and I don't have time in these tapes to present it 2 different ways most of the time. So think about that. This I to the 34th power, I'm going to think of as I to the 32nd times I to the 2nd, because those two factors, their exponents add together to be 34, and this one right here is divisible by 4. You know, again, just in case you're thinking this, I would never choose a 28 here and a 6 here. I need to get the even number that is just below 34 that's divisible by 4. Again, this is equal to 1. This is equal to a negative 1. Let's go ahead to this next term, I to the 55th power. I want to think as I to the 52nd times I to the 3rd, because those two add to be 55, and the number 52 is divisible by 4. If I had used a 54 here, 54 is not divisible by 4. Any I variable raised to something that's divisible by 4 is equal to 1. I have memorized that I cubed is equal to a negative I. Now I can prove it to myself too. And what I have here is 1 times a negative 1, which is a negative 1, minus 1 times a negative I, which is a negative I. And when I want to subtract a negative number, I should always come down and say that I will add the opposite. So I will add a positive I. And here's the final expression for I to the 34th minus I to the 55th. It is this complex number, a negative 1 plus I. Another problem, just like the previous one, I want to break I to the 13 down into I to the 12th and I to the 1st. I like to write that 1 until you get used to this. These add up to be 13. I'll bring my 7 down. Let's go over here to the I to the 11th. I'm going to write that as I to the 8th times I to the 3rd. Again, because this is divisible by 4, and those add to be 11. Again, please remember anything that is I to some power that's divisible by 4 is equal to 1. So I have a 7 times a 1 here. That's just 7 I. And then here I have a 5 times 1, which is just 5. And I to the 3rd power is a negative I. So this minus 5i here, this is 5 times a negative I. It's a negative 5i is what that is. But I want to subtract that. And whenever I subtract a negative number, I'm going to add a positive number. So I have 5i and the 7i in front. And this one turns out to be a complex number that results in just an imaginary term. The real term here is 0. I could read this as 0 plus 12i is the answer. But interestingly enough, sometimes several terms will simplify down into just one term, and that's perfectly acceptable, and it's going to happen. When working with complex numbers in this section. So far we have added and subtracted. That was a matter of combining my like terms when I'm adding. When I'm subtracting, I had to add the opposite and then combine my like terms. And we multiplied. We distributed, we used FOIL to multiply. We combined terms. We took those terms that had I squared in them and replaced that with a real number. Now what we're going to do is we're going to divide. So we're going to have done all 4 operations. To divide 2 complex numbers, what you're going to do is you're going to multiply by the number 1. Whenever you multiply anything by 1, you have the same thing. And that's why we're allowed to do this. But the form of 1 that we're going to use here is going to be in a binomial on the top and on the bottom. So we're going to multiply this by a fraction. But the binomial that we're going to use is the conjugate of the denominator. So I have 2 plus I here, so I'm going to multiply by 2 minus I. But I have to do that top and bottom because I am multiplying right here by 1. Please put parentheses around all of this because you got to FOIL it now, is what you got to do. And just be careful, collect your like terms maybe in your head. I probably am going to do that in my head. So 2 times 2 here is 4. Here I have a minus 2i and a plus 2i. Please remember when you multiply a complex number by its conjugate, the middle terms are going to add together to be 0. That's what happens just now. And a positive I times a minus I is a minus I squared. This one's interesting because there's no number in front of I squared. That's been the case most often. This denominator, I'm going to bring it down here, is 4 minus a negative 1 because remember I squared is a negative 1. And so I'm going to end up with a 5 in my denominator when I'm done with this problem. I like to do my denominator first because it's simple. When I multiply a complex number by its conjugate, I always end up with a real number. So I always like to do this first because I know I'm not going to have any I terms when I'm done. Upstairs, however, is a different story. 5 times 2 is 10. And then I have a minus 5i plus 4i. I'll write it down this first time. A minus 5i plus 4i. Again, right here's the minus 5i plus the 4i. And then my last terms will multiply together to be a minus 2i squared. So I've got to clean this up now. So, and I'm not going to do everything in one step. The minus 5i and the plus 4i gives me a minus 1i. And this minus 2i squared is a plus 2, please. Don't forget. That's a negative 1. Minus 2 times a negative 1 is a plus 2. The 10 and the 2 add to be 12. Minus the I always write a complex number with the real number first and the imaginary number second. I'm done. I've done the division. I have a complex number. I have a single complex number. It is 12 minus I divided by 5. Or I could write it as 12 divided by 5 minus 1i divided by 5. Sometimes I'll even write a 1 there. 1i divided by 5. And I can see the real part and I can see the imaginary part of that complex number. Sometimes I do this so that I can be sure to reduce my answer when I'm all done. This one doesn't reduce at all, so I can write it like this or I can write it like this. Again, you're going to be turning your test in paper pencil form for me. You give me one of those two. Let's do a couple more of these division problems. In this one I have a denominator of 1 minus 3i. So I have to multiply by its conjugate 1 plus 3i. One sign changes, you guys, the sign on the imaginary term. So I'm going to multiply this by 1 plus 3i, top and bottom. And I'm now not going to write all the steps of the FOIL process down. I'm going to do them in my head. So here I have 1 times 1, which is 1. And then the last terms multiplied be a minus 9i squared. And that's therefore, this right here is going to be a plus 9. So I have a 1 plus 9 in that denominator. So the denominator for my answer is a 10. Upstairs, 6 times 1 is 6. And then here I have 6 times 3, that's 18i. And a 2i, that adds to be 20i. And then 2i times 3i is 6i squared. Well, interesting. 6i squared is a negative 6. And 6 and a negative 6 add to be 0. And so all I'm left with then in the numerator is just that 20i. And what you have to watch and be careful to do is if these can be reduced, because either I have a monomial up above and a monomial down below where 10 goes into here once and 10 goes into here twice, or even that I have a common factor in the denominator that goes into both of the terms if they're real and imaginary. But you've got to reduce at the very end if you can. The answer to this problem turns out to be 2i because I lost my real parts up above when I FOILed. And if you're asking to divide by a monomial, in this case I'm asking you to divide by 7i, I multiply by its conjugate. But the conjugate of 7i is a negative 7i. It's the opposite. So I just need to multiply this top and bottom by a negative 7i. And what I get downstairs here is a negative 49i squared. And remember, I squared is a negative 1, so a negative 49 times a negative 1 is a positive 49. That's what I have in my denominator. Remember, we've said that if you multiply a complex number by its conjugate, you always get a real number. There will not be an I term left. And 5 times a minus 7i is a minus 35i. I do have to be careful to reduce this problem. I'm done, but I see all of a sudden that there's 7s that go into each one of these. So I'm going to say that 7 goes in here 7 times, 7 goes in here 5 times. Remember, it's a minus 5i that's up here in the numerator. So I will reduce this to a minus 5i over 7, and we're done. We've finished looking at adding, subtracting, multiplying, and dividing complex numbers, and we also did some simplifying where the imaginary numbers were raised to very large powers. All we're going to ask you to do now when it comes to the realm of complex numbers is to take an answer that's given to you for an equation and check it and see if it works in that equation. So in this problem, I'd like to see if a negative I is a solution for this equation, x squared plus 1. So anywhere I see x, I want to plug in a negative I. So I want to take a negative I, and I want to square that. Well, the negative I times the negative I is a positive I squared. And I squared, we have said, it's been defined, is a negative 1. So I'll replace that. And on the left-hand side, a negative 1 plus 1 is 0. And I can say that a negative I is a solution for this equation. It won't be this semester, but it will be in your future semesters if you choose to continue to study, where I might be solving equations like that will result in answers that give us imaginary numbers. And I should go back and check those. This is the last problem that I'd like to share with you in Chapter 6. I want to know if 1 minus I, the binomial, the complex number, is a solution to this equation, x squared plus 2x plus 2. So anywhere I see x, I'm going to plug in here 1 minus I. So here's x squared. Then plus 2 times x is 1 minus I. Bring down this 2 here. Bring down your equal sign. Bring down the 0. And just do the algebra now that ensues here. So I've got this binomial that I want to square. Just in case, I'm going to write it out twice. And I'm going to deal with that right now. When I ask you to take 1 minus I squared, I'm asking you to do this. This product right here is 1. Then this is a minus I, and a minus I is a minus 2I. And a minus I times a minus I is a positive I squared. And now I'm going to distribute a positive 2 over here. So I'll have a positive 2, and 2 times a minus I is a minus 2I, plus 2 equals 0. So I've done all the multiplication here. I've gotten rid of the parentheses, really. Now what I want to do is I want to collect my like terms. Well, I'm going to notice that this I squared, which is equal to a negative 1, could be added to this 1 and would give me 0. So I'm just going to cross those off. 1 and a negative 1 add to be 0. This 2 and this 2 adds to be 4. And this minus 2i and this minus 2i collects to be a minus 4i. So I've collected and or added terms together that add to be 0 on the left-hand side. Everything is collected. And I want to know if that expression is equal to 0, and it's not. So I would come back here and say that no, 1 minus I is not a solution to this equation. And that's all I was looking to have you do. In conclusion, for this chapter, there's a lot here. We began back with simplifying radicals way at the beginning of this chapter and working with exponents, radicals written as exponents, and multiplying, etc. I feel very strongly that this chapter is hard to take the test online because you have to type in negative exponents and you have to type in roots of numbers, third roots and fourth roots. So I'm going to be sending you the test that you need to take over this chapter by email, and it'll be an attachment. The hitch here is that I think it's wrong to let you have 2 weeks to take a test. So in other words, to send you the email on Monday and say, here's your test for Chapter 6, send it back in 2 weeks. Since traditional students who attend a traditional classroom, you have to take it on the spot, in person, in an hour and a half. So I'm still going to give you more than they get, and that I'm going to give you your test. I'm going to send an email to you at 8 o'clock in the morning on the day that you request it. You have to request it in advance. Don't expect me to wake up at 7 o'clock in the morning and send you a test because you just wrote me an email by 8. Anyway, you give me advance notice. You tell me which day you want it at 8 o'clock in the morning before the due date, and you have to get it back to me by 8 o'clock in the morning the next day. You can, if you're on campus, just put it underneath the door of my office, which is in the classroom building, room 55. You can send it by fax. You can scan it and attach it in an email, or you can put it in the mail. I would highly suggest you use that as a last resort because I'm going to be checking the postmark date. If it's not postmarked by 8 o'clock in the morning the next day, you're going to be substantially penalized for not turning that test in within 24 hours. If you have any questions, give me a call. Good luck on this chapter.